no, the ship is about to crash. We have to stop it now. And only seconds to go. Boy, is it a good thing that we got that ship stopped. Welcome to today's walkthrough as we go over the lab of torque. Now, in this lab, we're going to be basically studying the conditions for static equilibrium. But before we dive in a little bit deeper on that, let's take a look at this week's pre-lab activity. In this week's pre-lab, you're asked to take a look at how a force acting on an object far away from a position where it can rotate around, a bit different than what we did before, is what you're exploring. And you can do this one of two ways. One way is to go to a door and just push on the door according to the instructions that's in the lab manual, or another one is to use a handy bag to help illustrate the idea of torque. So what you want to do is just simply place the object in your hand and hold it far away, and then move it to different positions and just kind of get a sense of how heavy it feels at those different positions. Feels like a little bit of a cheat to have it on the shoulder, but ask yourself the question, why is it such an easier task if that's how it feels versus out here for an extended period of time? Then you want to draw the free body diagram, and if you're not familiar with how to use the free body diagram, make sure that you watch the theory here shortly about drawing free body diagrams for torque situations. Once you've had a chance to take care of the free body diagram and consider the force acting at distances far away from yourself, then that's it. You're done with the pre-lab. Let's take a look at the theory. In order to talk about torque, we need to talk about, once again, one of Newton's laws, Newton's second law in particular. Because we remember pushing on an object with a force, we apply the force and we draw it with the force acting at the center of the mass. We treat it as a point mass. We've been treating everything as a point mass this entire term, and now we say let's branch out from there. So we apply Newton's second law at the center of mass of an object, and the acceleration goes along the direction of that force, and we have Newton's second law as a observable cause-effect situation. So what happens though, if we have a mass that's at a fixed location and can rotate, and we can give it some push or pull along that path, that makes it go on a circular pathway? And the answer is, we have applied a force at the point of mass. We're going to assume this part is massless or doesn't factor into the calculation we're looking at just for the moment. And we see that it is some radius from the point that it's going to rotate around. We'll eventually call that a pivot point. But this point of rotation, and that force acting on it, is going to lead to it following a curved pathway at some angular acceleration. And that corresponds to some characteristic motion that's happening in this circular pathway. Let's take a quick note of the fact that we have a force times a radius, because the radius has to be factored in here as well. And if we're going to multiply a force and a radius, we have to take into account that we're dealing with two vectors. Here's the catch. These vectors are 90 degrees to each other. This is not the same situation as when we were looking at work, which we were force times the displacement, both vectors, where we wanted the force and the displacement to happen in the same direction. Now we want what we're trying to observe to happen when the force and the radius are perpendicular to each other. So let's take a quick look at the vector multiplication that we need to use in order to take advantage, in fact, of this configuration. Okay, so now we've got to deal with the fact that we need to multiply two vectors now that are not facing the same direction. They're actually perpendicular to each other to get the most out of it. And so we go back to our vector algebra. This time we're looking at the cross product, also known as the vector product. The vector product is so called because in this case, when we multiply these two vectors, we get a vector at the end of the day. And so the idea is, remember, we want it to be 90 degrees to be the determining factor. So we look at the sign in this case, because we see at 90 degrees, that's when we have our maximum value on for our trig relationships. And so we say, if they're going the same direction, we want that to go to 0. And for perpendicular relationships, we want them to go to I cross j, somehow to result in a third vector. And as it turns out, beyond the scope of this conversation, it turns out that if you use what we refer to as the right-hand rule, that you get the k vector out as the third point. And a way to use that is to hold your hand up in such a way that my index finger becomes the x-axis, my palm or my other fingers bent in the direction of my palm are going to be the y-axis, and then my thumb forms the third k-axis, and so x cross y gives me k. And if you think about circular motion, when we apply for a radius and a force acting this way, we've got our thumb pointing in the direction of 1, and if we go the opposite direction, it rotates the opposite direction. So give it some thought, reflect on that a little bit. But going back to the mathematics here, a little bit of a proof. I cross j, we take the magnitude of those just like we did before, but instead of a cosine, we'll take the sine of theta, and then the resultant will be a k vector, a vector that's perpendicular to the plane formed by the x and y, or the I and j vectors. Put in 90 degrees, that gives us 1. The magnitude of each of these, of course, unit vectors, the magnitude is 1. And so we have 1 times 1 times 1 times the resultant vector k, and that's how we get this result. Back to you. Thanks for that. I always like to talk to myself. Who doesn't, right? So now we apply this radius times the force for Newton's second law, which gives us this expression up here, radius times force, radius times ma. Now, the stuff that's going on the right, we're going to take a look at in an upcoming lab activity, so you can take a look at moment of inertia lab for the theory on that. But we're going to stick to the left-hand side of the equation and take a look at what's going on there. Namely, we've got r cross f, and it leads to a characteristic behavior in that circular pathway. And so we're going to give it a name. We're going to call it torque. You've probably heard the term before, torque, which we're defining specifically as radius crossed into the force. Applying the mathematics we just took a look at, we see that the magnitudes of the radius and the force come into play, and we have a sine of theta because these are perpendicular to each other. We want the perpendicular, the 90 degrees, to give us our maximum value. Take note of the fact that when we group a certain way, this term right here effectively looks like the perpendicular component compared to the radius, the perpendicular component of the force, and it's going to be giving us that. So when this is 90 degrees, it's our maximum value. If it's anything less than that, we're looking at the component as we've drawn here. We've got radius coming out from this position we refer to as the pivot point. And at the point where the force is applied, for example, in this case, we have gravity acting downward on it, and it can swing through that pathway. As long as the force is acting in this direction, this is the angle between the force and the arm that's holding it up in place, and we can draw our little triangle and take the component there and draw it from that position. So this is the same component, and the length of that component, the amount that's actually contributing to its motion at that point, or the torque at that position, would be the gravity force of that mass times the sine of that angle. So what do we do with this? Well, just like before, we had Newton's first law, Newton's second law, and Newton's third law. Newton's first law is don't add nothing, don't apply any forces, or if you have any forces acting, make sure that they're all canceling each other out. And you have no motion, no velocity, or you have an object in constant motion. We're going to focus on an easier situation to deal with in this lab, and that's going to be one that's static equilibrium, specifically at rest. And so we have static equilibrium from before, Newton's first law, sum of forces in the x direction, sum of forces in the y direction. That's for linear physics, and it still applies here. But now we have an extra component that can help us solve a situation, and that is sum of torques acting on a body in such a way that there are different radii from it will sum together and lead to either constant velocity or zero velocity. So make sure you're keeping in mind that this could also apply if the thing was going in a constant circular pathway. The torques would then be, again, balanced. How do we draw the free body diagram? So let's consider this situation where I've got a pivot point and a rod, a long rod that has a mass that is balanced on that pivot point, and there are a couple other masses set upon there. Each of those masses, you'll notice, has a radius from the pivot point, what I've identified. Fun math fact, you don't have to use the actual point of rotation for the pivot point, but it does simplify the situation when you do use that, mathematically speaking. The radius going out to force 1, we'll call that radius 1. The radius going out to mass 2, we'll call that radius 2. There is a radius to the center of mass. Sometimes the pivot point's there, sometimes it's not, depending on your situation. And there's actually a force that I've not drawn here, a normal force, because this is all sitting on this pivot point, gravity pulling down. You draw the free body diagram. Well, this is not the free body diagram. First off, this is a sketch of the configuration. We can do an individual free body diagrams for each of the masses, including the long rod. We're going to focus on the long rod because that's going to be the part that actually rotates. These may not be fixed to that. They may be. It depends on the problem that you're working with. When we look at Newton's first law, the first two equations for this configuration, Newton's first law says if there are any sum of forces going in the x direction. In this configuration, we have no forces that are moving left or right. And so I've just got the object, the rod, indicated here as a ball. And I'm just writing NA. There's nothing there. So this is a nothing burger. Second, we look at the sum of forces in the y direction. There's a lot of forces acting. They're nicely spread out here. But remember, for Newton's first law for a linear component, we treat this as a point particle. So we've got the object. We've got the normal force because there's a force acting upward. We got three forces acting downward. That's going to correspond to the masses of each of those times 9.8. And the center of mass also drawn in here. And notice I've done my best to kind of draw them as from the center of this point. And then I've got my orientation of the axes, where's my positives, and acceleration is 0 in this case. This is your complete free body diagram for the vertical motion. Finally, sum of torques in this case, we look at this, we say, okay, I've got the rod that goes this way. Notice that's just this rod right here. These are the radius lines here. I've indicated my pivot point. And around the pivot point, I like to indicate the positive direction. So we use a convention that from positive x in the counterclockwise direction, we get a as going to be our positive reference. Does that have to be that way? No. Again, as long as you're consistent throughout the course of your calculations of a particular problem, whatever orientation you pick will work just fine. But we're going to use this as positive. We got the normal force drawn here at the pivot point. I've got radii drawn to each of the three vectors that are hanging from the thing. There is, not drawn here, there is a radius vector to from the pivot point to the normal force. The radius is 0, so the pivot point, the normal force in this case, contributes 0 torque to the configuration. If I put my pivot point anywhere else, especially, remember that this is static equilibrium, so the pivot point doesn't matter because it's not actually physically rotating around it, it just can rotate around that point. So wherever I've got the pivot point, I can have the force act at that radial distance. The normal force that I've drawn here, the normal force is acting at the pivot point, therefore the radius would be 0, the torque contributed by that would be 0, and just generally gets swept to the side. Radius, force of the center of mass, radius times force of each of these. And you'll notice that each of these are 90 degrees. So the sine theta, probably a good exercise to include the sine theta as being 90 for the first couple of writings. And then once you've internalized that, just make sure that you're aware that that's what's going on in this configuration. The setup for this lab activity is fairly straightforward as far as equipment goes, but let's go over some of those items right now. Number one, you're going to be dealing with a ruler, which is, in this case, this is an aluminum ruler. You'll notice it's different from the wooden rulers you've been doing. In particular, it's not bent. It's a very well machined, very straight device, so we won't have to worry about any curvature in the material. Plus, also, the fact that it is aluminum means that as we fix the components to it to hold it fast, it won't cause any bends or dents in this. Our main concern is going to be worrying about over tightening on those. So hanging on this are going to be these various hangers, as well as the central fulcrum, which will run through like so. And you'll want to align very close to the center as you can, and just give it a little snudge. It does not need to be super tightened, just finger tight is sufficient. And then this can wobble on that. If you see any signs of significant friction on there, make sure you let your TA know, and we'll make sure to clean it up. But you also have on this a level that you can use to see how well leveled your whole system is. Even though in a static equilibrium, the configuration is such that you should not need to necessarily have it exactly level, it keep trying your best to make sure your system is level when it is balanced. If it's not level, try and move it to a position of being level and check your stability at that point. These hangers slide on just as you can see, and you can tighten them up to the radial position that you want them to be, and you can hang your hanger masses from this swinging point. You also notice that there is a protractor built onto these. Let's see if we can get good lighting on that. It may not be obvious in the picture, but these do have protractors built on there with a 0 at the perpendicular, so all the angles are measured relative to that perpendicular angle of 0. Again, a way for you to check to see that you are in fact not only in static equilibrium, but that your configuration aligns with traditional axes, X and Y axes. At your station will be masses very similar to these, where you have these hooks, but a special feature is that they have hooks at the bottom, so you can take a second mass, hang it on there, and then the two can be in combination to each other to give you various particular masses at various positions along there, and then again you can just hang it on the hanger when you have it in place. This lab does not require you to use capstone, so they won't have any electronic configuration set up for this. This is all about radial distances, forces applied, and making sure that things are perpendicular and making the most out of your configuration in a static equilibrium. When you arrive, you'll find your setup very similar to this, probably not with these on there already, but in this similar way. And what you'll notice is that it's lined to be just right aligned with the edge of the setup. So you kind of have a catching space here, but you want to be careful so that the masses don't fall down and create a little bit of chaos in the process. So remember that this does not need to be super tightened, but what you do want to come in and do is just kind of give it a little bit of nudge at the beginning, see how much friction there is already built in, and make sure that it's exactly balanced. You don't want it to have way out here and seem like it's balanced. You do want to be able to demonstrate that it's going to rock. That lets you know that this is not actually balanced until we adjust it to just right at the center. But you do want to make sure that you get the mass of this before you proceed. So you're going to take this back off, reset this back up. And you're only looking for the mass of the rod, not the center hanger here. The reason for that is because this mass is presumably centered on either side of the fulcrum point that's in there. And so knowing that mass does not add to your configuration. Notice that we also have your setup that this ruler, very similar to how it looks on the paper, or the demarcations are on the paper, so you can help you draw your free body diagram better. So 0 is measured over here. Place your first object like so at a point designated according to the lab manual. Before you hang the mass on that, go ahead and put your hanger on the other side. Again, this is going to move freely, so make sure that you are conscientious of that. You want the screws on the top so that the hanger can hang loose, and use the protractor that's built in onto these hangers. And then you put a mass on according to, the instructions in the lab manual. And you say, well, what's the mass that will balance this out? That doesn't seem to do it. And you can adjust this accordingly to see if it does a better job of helping to balance. And if it doesn't, you take that mass off. Let's go to 200 and say 10 grams. No. Let's say 220 grams. And it looks like it's in balance, but again, this is not equal, so we want to balance it and give it a little bit of nudge here and there and see what it does. You see it does kind of a little bit of a favoritism towards that way, so this may be friction, maybe allowing it to look static even though there's an imbalance. That will decrease your percent difference, percent error. So we'll adjust this and maybe bring it in just a little bit. Doesn't have to be a big move. You see how it more or less goes. It's still kind of favoring this side, so we might move it in a little bit further and continue on that way. Part of your calculations are a little bit peculiar because we want the radius from the pivot point to the point where the force is acting. You can measure that directly and subtract in your mind, but I've built into the worksheet the ability to get that more precise without estimation or requiring you to rely on mental math and keep track of decimals and so forth. So you measure the position of everything relative to the starting point over here, and so your X positions are based off of this, and then you subtract the difference. So the X position to the fulcrum and X position to force 1, the difference of those is going to be your radius, and the sign will come from based off of where they are located. on this meter stick. For your final configuration, you place the mass at some position close to the axis, close to the edge, and then you adjust the pivot point until your system is balanced. And it takes a few moments, but once you find that point, you mark it. This is now your new pivot point. This is not the center of mass. This is the pivot point. Your center of mass is still here for the meter stick at the 50 centimeter line. So you need to keep that in mind when you're doing this last part, and notice that we're looking at the difference between these two positions to get this radius, the difference between these two positions to get this radius to the center of mass. You have a force acting downward on the center of mass as though this was an empty frame, massless frame, and all the mass of this is balanced right here. Okay, well, that's it for today's walkthrough, but don't be fooled. This can be a real pain in the neck trying to get them to get into static equilibrium and confirm that's exactly what you have. In the meantime, I think I'm going to go ahead and use some torque and put this boat back in action, and see you in the lab. But what happens? You can come all the way in, that's fine. You can be in the screen. When I push it, it seems to work better when there's not something in the way. When I push it perpendicular. Well, hope you enjoyed. Dang, I keep doing that. I hope you guys enjoy these PreLab walkthroughs. I can't even say anything. Okay. Sometimes you get over there and I'm like, I just don't really feel like talking right now. Okay. Wow, I gave absolutely no consideration to lighting. I'm gonna have a dark segment right here. I just was like, there are lights. All right, let's see here. So let's take a quick look at the algebra. Keep getting it wrong. So let's take a quick look at the vector amount. Get it right. Okay. And then always have to do something goofy. It's what the fans want, man. It's what the fans want.